Assalamu alaikum. This is interactive paging concept visualization and simulation using web-based technologies. Our team members are BOYU, Mohammed RAHMAN, and me, MUAADH ABDULAQAWI, and AQIL DZARFAN bin ASRUL Sharif. Our lecturer is Dr. Muhammad Faisal bin Muhammad Siddiq. So, let me start by introducing paging. Paging is a fundamental memory management technique used in modern operating systems like Windows and iOS. It works by dividing the logical memory into units called pages and physical memory into frames. The key benefits of paging are that it eliminates external fragmentation and allows processes to be loaded into memory in a non-contiguous way. This improves memory utilization, system stability, and security. By abstracting physical memory, the operating system can provide each process with the illusion of a large continuous address space while safely sharing underlying hardware resources. However, despite being a core topic in operating system, paging is often considered abstract and challenging for students. The main problems we identified are, first, students struggle to visualize how a logical address breaks down into a page number and offset. Second, they have limited understanding of how page tables store mappings between pages and frames. Third, there is confusion about the role of valid and invalid bits in page tables. Fourth, page hits and page faults are poorly explained. Students don't understand when they occur or why. Finally, there is a lack of interactive learning tools that allow students to experiment with different memory usage scenarios. Without understanding these fundamentals, students struggle with advanced topics like virtual memory management and page replacement algorithms.
Moving on to our methodology and system design, we approach this project through a systemic development lifecycle consisting of 4 key phases, which is analysis, design, implementation, and evaluation. For our system architecture, we adopted a client-server model to ensure a robust and scalable application. On the back end, we utilize Express.js. This acts as our lightweight server environment, handling the application logic, routing, and initializing the paging data structures. For the front end, we built the user interface using EJS templating and Tailwind CSS. EJS allows us to dynamically render the page tables and memory frame based on the server's data, while Tailwind ensures the design is clean, responsive, and beginner-friendly. Here's a deeper look at our simulation logic that drives our visualization. We model the mechanism strictly according to the standard OS principle. When a user inputs a logical address, our system programmatically splits into two parts, the page number and the offset. This simulates the hardware address translation process. The system then uses the page number to index into the page table. This is where the core decision making happens. For the page shape, we check the valid bit. If it is set to 1, it means the page is currently loaded and in a physical frame. The system then combines the retrieved frame number with the original offset to calculate the final physical address. When a page fault, if the valid bit is 0, the system identifies a page fault. This visually demonstrates that the process is not in physical memory, perhaps due to an I/O call and needs to be swapped in. By animating this address breakdown and lookup process step by step, we help students to visualize exactly how the OS manages memory mapping dynamically.
My name is BOYU, and in this demo, I will present our page concept simulator. The goal of the website is to make the page easy to understanding by show how a logical address is translated into a physical addresses use a page table and frames. On the left side, we have the control panel, and on the right side, we have the what happened now card, show the current steps, the last translation, and the hit fault status. And below the table, we have the logical address broken down and the page table and the physical memory. Now I'm going to show the single logical address mode. So when I toggle this, we can see we can set the logical address, and immediately the logical address broken down shows how the split into the page numbers and offset use the page size. When I click the step, the system will check the page tables. If the page table is not valid, the target is a page fault. Load the page into a free frame. The compute the physical address from the page size plus the offset. The result is displayed in the last translation, and this shows the exact path from the logical address from to the page table frame and the physical address. Now I'm going to demo the sequential. When I select the LRU, it will switch and click the apply. It will reset all and switch to the LRU part. This is the algorithm be used. If I choose the FIFO, it will also switch to the FIFO. For the page after the page fault, the notice will show how the after the page fault, notice how the page table updates valid bit and frame numbers. At the same time, the frame table show which page was loaded and when. This is a virtual link, make it clear how the logical page mapped into physical memory. This simulator demonstrates the full page process, logic address, page table, lookup, frame the selections, and the physical address calculation. It also shows how different replacement policy affect memory behavior, make it very useful for the OS. That's all. Thank you.
Assalamualaikum and hi to everyone. So I'm going to describe our simulator, how it's actually working in different algorithm. Like we have FIFO, fast in fast out, then LRU, and also lastly we have OPT. So okay, this is the logical address we already mentioned here, and we actually take this logical address from our exercise, our lecture sheet. So if you look at the reference string, see this 70 is actually the page number. So I actually converted this page number to our logical address, and then we are going to use this logical address and see is our simulator is working fine or not. Because if our simulator is working well, then it will match with our result as our lecture sheet, and that means it can prove that our simulator is okay. So this is our logical address. So first logical address is 1792. If we click escape, so this is our current step one, and it actually convert our logical state address to split with our page number, and this is our page offset. So if we go to page number 7, so this is our page table. Here you see page number 7 actually valid, and page number 7 is inside frame 0. So let's go to our physical memory. So this is our physical memory, and this is our frame 0, and frame 0 holding our page 7. The chart, you will see the same thing. 7 should be in the first frame. So next is our 0 page number. So this is our page number 0, and you see it changed, and then our frame is actually 1. So page number 0 actually inside our frame 1. So frame 1 holding our page 0. Now page number 1 inside frame 2. So frame 2 holding page 1. And if you see that page 7, page 0, and page 1 all are new, so we didn't hit any pages or what actually called by our CPU. So that's why we get fault 3, and there is no hit. And then the next one, okay, so go for next one. Next one is our page number 2. So page number 2 is also different page, and it's stored inside our frame 3. So this is our 3 and holding page number 2. So this you can relate with the graph, like 7012, not graph, sorry, my bad, chart. So then we will get 0. Okay, let's click our run. So you see this is our page 0. So as we know that 0 already in our frame. So here, over here, our frame 1 was containing the page number 0. So you see there is a blue mark. It's indicating that 0 was here. That's why you see our hit also changed to 1. So as far we came to this point. So this point we get 1 hit and 4 fault, same as here. And this work like this way. Okay. So as is FIFO. So the next, you see our frame is totally full. That's why if we if we click here, then it will swap out the oldest one. So here our oldest one actually 7. 7 actually came to the memory first. So if I click here, this is my page 3. Okay, so page 3, and it will go to our page number, frame number 0. Frame number 0 based on FIFO algorithm. And this should be 3012. If you will check with our table, then you can see 3012, same. So it's work like this way and all the way. So I'm going to skip others because I already get the main point. We get 12 hit and 10 fault. Okay, let's check with our solution. So the star with red color is actually our fault. So we get 10 fault and 12 hit. So let's count 1. So our FIFO is working. Okay, let's move to OPT. This is our OPT, and now our physical memory is free. Our page table, there is nothing. So if I put a step, so 7, page number 7 actually in our frame 0, same as our FIFO is actually containing everything. Okay, third one and fourth one. So our memory is right now full. So here we are here now. So then we will get 0, and basically 0 already in our page 1. Frame 1. If I click, you see it's indicating that it's got a hit, and you see hit and fault 4. Again, if I click, it looked for 3, page 3, but page 3 was not here in my physical memory. That's why it's changed 7 to 3, because it's actually we actually count in this thing that string number, I mean the page number will not use for a long time, and those string will replace, like we was here 7012, right? So we need 3, but 3 will swap with 701 or 2. from 3, we can see that we need 7 only here. But if we're going to swap with 0, 0, 0 is, we need 0 here. And then if we want to swap with 2, 2 is here and 1 is here. So we take 7 as our element to swap it with 3, and then we swap with the 3. I mean, how actually the OPT algorithm works. And you see also here, ours is actually swap with this one. Okay, so next step, let's go with the next step. So I guess I already get the algorithm, so I'm going to finish my all the steps. So this is our final result, you see, and this is our page table at the end. So we get 8 fault. If you count our solution, and we got 14 here. If you want to count 13, 14. Okay, now I'm going to explain the LRU one. Same as previous one, so our memory is free, so let's fill it up. So until here, we got only fault. No, there is no hit. Then we will get 0. Okay, 0. And 0 was here in our page. So we got one hit. One hit. If you refer back to our chart, it will be easy to understand. And then if you go, our next page will be 3. So if we click, you see, our next page is actually 3. And 3 was not in our memory. Here, previously, it was 7. So in LRU algorithm, we actually look that which page is not using, or a page is not using for a long time. So for 3, if you refer back to here, okay, 3, if you see 0 immediately used, 2 and 1, but for 7 it used a long time ago. That's why we swap with 3. Okay, then we can get another hit for 0. Okay, so this is our 0 and we get the second hit, and then the next one will be 4. Okay, let's click here. Okay, so next one is actually 4, and you see we get a fault because 4 was not in our memory, physical memory. So for 4 here, for 4, we actually look back to previous, which was not 0, already used immediately, then 3, yeah, but 2 also here. But if you see 1, only that page used, sorry, not used for a long time. That's why we swap 1 with 4. And if you refer back to our simulation, you can see 3, 0, then this one swapped because you see it's highlighted, and 2. And then we will get a lot of, heat. Okay, so you see it 3, then E4, E5, E6, and so on for the rest. Okay, so I'm going to make it fast. We get the result. So this is our fault. If you look our solution, we get fault 8, and we get hit 8 hit, 13, 14. We get 14 hit. So thank you. This is all my part.
In conclusion, our project has successfully met its primary objective, which is transforming the abstract and often difficult concept of paging into an engaging interactive learning tool. Ultimately, we believe this tool bridges the gap between theoretical textbook definitions and practical implementation, effectively solving the educational challenges we identified at the start. Thank you for listening.